Okay. Taking a look here, exercise 5. Working off those ideas of those equations where we have, Q surroundings and Q system here. So if the surroundings lose heat, then that means the system gains heat. If the system loses, that means the surroundings are going to gain, okay, like so. This case, we're taking 2 cups of water, 100-gram sample of each, or 2 beakers of water. One has been heated to 90 degrees. The other one is at 10 degrees, so it's been cooled. Taking the 2 of them and putting them together, okay? So, thinking about this, the final temperature of the water, is it between 50 and 90? Is it right at 50, or is it between 10 and 50? Any ideas here? Well, let's take a look here. Okay, I'm going to call this one water 1. The other one I'm going to call water 2 to kind of frame it. We're combining them together. So we have water 1, we have water 2. Water 1 is starting at 90. So is water 1 going to be the one gaining heat, or is it going to be the one losing heat? It's going to be losing. Good. Now, we have a 100-gram sample. We know it's water, so the specific heat is 4.184 joules per gram degree Celsius. We know these factors. All right. So for this case, I'm just going to say the Q for water 1 is going to be negative. The Q for water 2 is going to be the positive one, like so. So this is going to be the negative MCAT. So I'm going to substitute in for the Q, the MCAT over here. Substitute in over here the MCAT for the other water, like so. Now, based off of this, what 2 variables can I cancel? Or what variables can I cancel here? Looking at our information. The masses are the same. They're both 100. So I'm going to be able to cancel those out. They're going to equal each other out. The specific heat, because they're both water, and they're liquid water because they're in the liquid phase. Remember, it phase changes at 0 and it phase changes at 100. So the definitely the same specific heats here because they are in the same phase. So really the only factors here happen to be the change in the temperature. And remember, delta T is T final minus T initial. We do not know the final temperature. That's kind of what we're trying to eyeball here. But we do know their initial temperatures, 90 and 10. So we're looking here. This is going to be T final minus 90. And this, remember, has the negative. Don't forget your sign here or you're going to mess that up. That side's losing heat. Over here we have T final minus 10, which is the initial on the water 2. Okay. Now we could solve for the numbers. If you look here, this becomes negative TF plus 90. Over here, this is still TF minus 10. So if I move the 10 over here, I'm going to move that over here by adding, move the TF over here by adding as well, like just regular algebra. So then we're going to end up getting 100 equals 2 TFs, right? So divide by 2. And so the final temperature is 50 degrees. Does that make sense? That's how mathematically to look at it. But for this particular one, if you weren't wanting to calculate it, they have the same grams, they have the same degrees Celsius, so they should split right down the middle. And it should go right to the middle heat area. So the difference between them would be, 40 degrees on each side. So that's where you would land at 50. This is what happens when you're combining different objects at different temperatures. Objects that are not going to react with one another for these particular exercises, these are just hot objects with cold objects, so the heat flows from the warmer object to the colder object. So we had two objects of water, we had 100 grams of each, and we combined them. The heat flowed from the 90-degree water to the 10 water, and then they resulted in thermoequilibrium at 50 degrees there. Okay, so finally equaled out once everything was mixed. The thermal equilibrium resulted at 50 degrees. That was the same temperature for the 200 grams of water that were now combined. That also means that at that particular thermoequilibrium, they all have the same average kinetic energy at that point because it's the same temperature. That particular concept has not is not any different than when we used it in gas laws. It's at the same temperature, it has the same kinetic energy. Okay, so now we're going to look at different idea here. Still have two samples of water. What's the main difference in this particular exercise 6? They have different masses. So now we can't really just cancel out the masses. What can we still cancel out? We can still cancel out the specific heat because, yeah, the specific heat is still the same for both. So C is able to be canceled. Once again, it's best to give yourself the frame of we're putting these things two together, and since it's heat's being gained by one of the objects, heat's being lost by one of the objects till they reach thermoequilibrium. All right, so I'm going to call this one water 1 again, this one water 2. Okay, so water 1 starts at 90, water 2 starts at 10. We know the 90 is going to lose. So, water 1 is going to be, the Q that loses. This will be the Q that gains. Okay, then we do our MCAT. So now we have negative MC delta T over here. This side is going to be the gainer, so that's going to be the positive. The C's cancel because we know that it's still the same specific heat, but we do have to enter in our masses. So on the losing side, that one starts with 100 grams. And then the change in temperature is still final temperature minus initial. The initial temperature was 90. Over here, the mass is 500 this time. And the final temperature minus the initial. Now we kind of have it set up to where we can calculate for the final temperature. Although, if I'm just eyeballing this, I could probably figure out which choice, A, B, or C, to choose. Looking at it, which one do you think it's going to be? A, B, or C, without doing the math part of it? Should be C, because the colder water, there's much more of it, right? So it seems more reasonable that the final equilibrium, thermal equilibrium temperature would be closer to 10. Right? Does that seem reasonable assumption to make? Since it's more massive, the colder is more massive, that the temperature should reside more on the colder side, closer to the colder initial temperature. So yeah, I would select C without even having to do the math, but we're just demonstrating the math, which is good. So then you have to distribute, and this is where it gets so not fun. So this is negative 100 TF plus the 90. Okay, now you got to watch that sign, because if you get the sign messed up, the math does not work. All right, so this is 500 TF minus, oh wait, sorry, this is 9,000. I can't multiply today apparently. 100 times 9 is 9,000. Thank you. I guess you could. I mean, that's definitely, well, we can check and see if that works. I assume it would mathematically. Thinking about it, yeah, probably. Although, to me, that messes up the signs in my head, so I do it this way. And this is 5,000, sorry. All right, now move over. This one moves over here, that's 600 TF. This one moves over here, that's 14,000. And then divide TF ends up being like 23.33, whatever. And since these are two, I'm going to stick with 2 digits here, so I'm going to make it 23 degrees Celsius, which definitely falls in between here. But you can go ahead and try that divide first. I mean, algebraically, I think it works, but once again, I'll get my signs all messed up. So I just kind of do the distributing way, making sure I'm making my signs. Yeah, so I'm sure it works. Whatever works for you, just as long as you end up with the right answer with the right sign kind of thing in place. There you go. So this one's another, example of this thermal equilibrium. You're adding 2 objects together that don't react with one another, and they're just transferring heat between each other. Okay. We're going to look at some reaction ones later, and that's going to be getting delta H's of reaction. All right, now this one takes a little bit more because it's wordy. You got to read through it. So take a moment to read through the question. We'll go over it in just a second. Looking here, substances A and B. A and B. Initially at different temperatures come in contact with each other to reach thermal equilibrium. Important fact there. Mass of substance A is twice the mass as substance B. The specific heat capacity of B is twice the specific heat capacity of A. Statement is true about the final temperature of the 2 substances once thermal equilibrium is reached. Who figured it out? Who knows the answer? What is the answer? C is an excellent choice because it happens to be the answer. Now, some of you, like I said, aren't going to mentally see this just yet. It's not going to work out exactly in their head. So when this happens, do the concrete here. We have substance A combining with substance B together. Now we can just decide substance A is the hot one that's going to cool, so that's going to be the negative. Substance B is going to be the one that gets the heat. It doesn't really matter. You can assign it to whoever. But what you should realize then, so if this is, this tells us that twice the mass, so this is 2 times M, C delta T. Over here on this side, substance B, okay, it says the heat capacity is twice that. So it's going to be M2C delta T, right? So what can we cancel out here? What do we know is equal and we don't really have to fuss with? Well, the 2, okay, but like all of these values, right, when you do the multiplying, right, they should cancel, right? So there you have it. So that means really we're dealing with negative delta T for A equaling delta T for B, and that would be T final minus T initial. And this would be T final minus T initial. Now, if you're still having trouble visualizing that now it's going to end up in the middle between the 2 temperatures, which it would, you can give it temperatures. You can be like, okay, if this one starts at 100 and this one starts at 20, okay, then you know it's going to end up right in the middle between the 2 temperatures. Because we've already done this problem. We did that in exercise 5, right? So the difference between the 2 is 80, so it would be 60. So 40 on either end. Add 4, subtract 40 from the 100, add 40 to the 20. It's going to end up, being 60 if I put in fake numbers. You can do that. You can put in fake numbers. You can't visually see what they're doing based off of what the description says. Write it out. Use the equations. Plug in your own values. Okay, you'll see the relationship that ends up working itself out here. Does that make sense? So definitely apply the equations if you can't see it in your head. So twice the mass, twice the specific heat. Basically, you're multiplying both sides by 2 then. So the mass and specific heats are going to cancel. And here we go. Okay. Last example here where we're not using water and water. So now we're taking a piece of hot metal and putting it into water. So this is still 2 objects. We're just transferring heat between the objects. They're not reacting with one another. So this is an MCAT problem. When you have just the 2 objects combining, it just becomes an MCAT problem. Styrofoam cup with 50 grams of water at 20 degrees. You add the 10-gram iron ball at 300 degrees Celsius to the water. And they gave us the specific heats, of course. Obviously, they would need to do that. Now, noticeably different specific heat for iron. It is considerably lower. So, the hot iron ball, even though it's at 300 degrees, its specific heat being so much lower, it's not going to make that much of a difference in terms of the heating of the water, since the water has a much higher specific heat. So based off of that assumption, don't really have unless you like work it out, you don't really have a good idea of exactly where it's going to fall. I mean, I think it's going to fall in the C range because water has such a much higher specific heat, and that even that, small amount of iron, it's like only 10 grams of the iron at 300 when it reaches the thermoequilibrium. Is it really going to raise the water over 50 degrees? Probably not, due to that low specific heat. So here, I'm going to set it up again. Make sure that you're taking your 2 objects and thinking about where they are. So, we have the Q of the water and we have the Q of the iron. Okay, which one's losing, which one's gaining? I need to make sure I assign my signs correctly. Is water gaining or losing? Yes, iron is losing. Good. Water is gaining. Very good. So this side gets the negative. The water's gaining, so it's positive. You don't have to put the plus there. I just do it to help me remember my signs. So this is the positive MCAT over here, and we're using MCAT because these are measurements that are in grams. Now they could give you these also in moles, so you might have to use the NCAT version of it rather than the MCAT. And this side would be the negative MC delta T over here. And then it really is just plug and chug. I do the math. I'm going to kind of do that down here where I have more space. So I do the 50 grams of the water times the 4.18 joules per grams degrees Celsius. The final temperature, I don't know, but the initial temperature of the water was 20, so 20 degrees. Over here, I have 10 grams for my iron, and don't forget my negative sign out here, 10 grams, and then my specific heat, low specific heat, 0.45 joules per grams degrees Celsius. Still don't know the final temperature, but I do know the initial temperature is 300. Now I can start doing the calculating. And like I said, it becomes a big algebra mess. And, if you want to go ahead and divide stuff out differently, you can. I'm going to multiply and then distribute. That's how I work these problems. So I get, for this 2, I get 209 times the TF minus the 20. And so this will be 209 TF minus 4,180. Over here, This is going to be negative 4.5, the 10 times the TF minus 300. Now I distribute, so this is negative 4.5 TF minus 4.5 times 300 gives me 1350, except for this becomes positive, 1350, because negative times negative gives you positive. Yeah, for this particular problem, you would have to be able to use a calculator. They couldn't give you easy enough numbers to work with this one. So yeah, I would say if you're given this type of data, it's going to be in a free response. It would not be in a multiple choice. The kind of multiple choice question they give you is like exercise 7, where they give it to you like in a description like that, where you're supposed to kind of mentally figure, where you don't really have to use numbers. So that would be more of an example of a multiple choice question. So that's good. Good question. So I'm going to move this over, add the 4.5 TF to both sides. Just like in algebra, that cancels. Then I would add this to both sides. That cancels. So then I end up with the 209.45. This is 213.5 TF equals the much larger number over here on this side. This is 5,530. Divide, and you get your temperature. And that I'm getting for TF 25.90 something, whatever. This one has 2, this one has 3. So I'm just going to go with 26 degrees Celsius here as my final temperature. So that does put it at C, in between the 10 and the 50. And the remarkable or notable thing there is because the specific heat of the iron is so much lower, even though it's at a much higher temperature, it really doesn't raise the temperature of the water all that much. Only 6 degrees. All right, dissolution reactions, or dissolution and reactions. So this applies to dissolving things in water and also reactions that take place in water that are in aqueous solution. Now we're going to start looking at finding delta H's and using the calorimetry data to find delta H here. First thing though that we should point out and look at is what type of process is going on here. Is it exothermic or endothermic? If the two reactants, or say the salt and the water, when you dissolve them and it gets warmer, this means it's exothermic. Now the dissolving process, remember, they are still, even though it's a physical process, they're still overcoming the forces. You know, if it's a salt, they're overcoming the Coulombic attractions between the positive and negative cations, and of course overcoming the hydrogen bonding in water to establish that ion dipole force between them. So in a way, they are still overcoming and breaking and rearranging forces here. So if it warms up, though, it's exothermic. If it cools down, it's endothermic. Now, why is this? The important thing is to remember here about your thermometer. Where is the thermometer or the temperature probe located? It is located in the surroundings. So it's measuring from the surroundings perspective. So what's going on in the system is opposite. So if the heat is going up and the temperature is rising, that means the surroundings are gaining heat. That means the system's losing heat. That would be exothermic. If it's cooling down, that means the surroundings are losing heat and the system is gaining heat, and that's why that would be endothermic. It's very important you pay attention to that thermometer. It's opposite. Temperature goes up, exo. Temperature goes down, endo. In these particular, looking here at this way that delta H works. It actually helps make sure our delta H gets the correct sign as well. Now, the equations we use here. Okay, I threw in the reaction with the solution, the reaction that takes place in solution idea here. but the kind of the same concept applies. We're going to be finding QAQ. What's happening? Where's the heat that's going into the water? That's going to be considered the surrounding, the aqueous solution. Now, one thing you have to note here is going to be the mass of the solution. You have to add the mass together here, the entire mass of the solution, in order to know the amount of heat that's evolved or the heat that's absorbed. So QAQ is considered from the surroundings perspective. Q solution or Q reaction, if you're talking about it in terms of a reaction taking place in an aqueous solution, it's going to be the opposite sign. So say, for instance, negative QAQ, that means that the temperature dropped, so it's endothermic. So the water got colder, basically, in the process of this dissolving or reaction. That means Q solution is positive because the system gained that heat. Same is true here. So if QAQ is the positive, that means Q solution or Q reaction is going to be the negative. So if the watery environment is gaining the heat, that means the system's losing the heat. So it's the opposite sign for the Q solution reaction. This is really defining, this is the system, this is the surroundings. Okay. Now, the extra added step here with these types of problems where they're using the calorimetry data, you have to find delta H. And this could be delta H of solution or reaction, either one. And you're either going to find it using the mole of the solute that's dissolving or the mole of the reactant that is reacting. So you're going to take that into account to find the delta H of either that particular salt or that particular reactant. This is the important equation at the end that you must know. It's not on the formula sheet. Basically, you take the heat divided by the moles and you're done. Q is the heat. But calorimetry here, once again, if you're reacting or dissolving, that thermometer is going from the surroundings perspective, so you have to change the sign in order to get the correct delta H, the correct direction of the heat flow. Let's look at an example real quick. We have 1.34 grams of KVR dissolving in 74 grams of water. Coffee cup calorimeter, the temperature drops from 18 degrees to 17.279. Assume that all the heat absorbed in the dissolving process comes from the water and that the specific heat of the solution is the same of the water. So they told us the specific heat 4.184 joules per grams degrees Celsius. Now there's a reason why it's the specific heat is measurable as the same as the water here. And that is because if you're looking at the amounts here, you have 1.34 grams of the salt, but you have 74 grams of the water. You have much more of the solvent here. So it really takes on the same specific heat as the one that's in the huge majority. So the water being in the huge majority, the specific heat's going to be almost directly on that same specific heat of just regular pure water. All right, so let's start with the first one. Is this exo or endo? And how would I know? What can I pinpoint here in the problem that makes me automatically be able to identify that? Definitely endo. And how did you figure that out? What were you looking at specifically? It cools, yes, temperature decrease, exactly. It even says heat absorbed too, that's also a point. But I always hone in on looking at the temperature. Did it go up or did it go down? Temperature went down, that means it cools, that means it's endo. So pay attention to that temperature drop, endo here. So this would be the answer to the first one. I always look at the temperature. But it does tell you heat absorbed. It does tell you in there as well. Now it says calculate Q solution for this process. So we can't find Q solution till the end because actually we have to start with finding QAQ to begin with. Because we need to find from the surroundings perspective. So QAQ equals MCAT. Now remember, the mass isn't just the mass of the water or the mass of the solute. It's actually the combined mass of both. So you would need to add these two together first. Okay, add those two together. We need the combined mass. Uh-oh, I did that wrong. I'm getting what? 75.34 grams. Did you get that? Now technically we should just use 75.3 because that only goes to the tenths, that goes to the 100ths. So I'm going to put that in there, 75.3 grams. Specific heat they told us was the same as the water, so I'm going to put that in here. Now the final temperature, 17.279. 17.279. Oops, don't need the parenthesis yet. Subtract the 18. So as you can see here in this particular part, it's going to end up giving us a negative QAQ, right? So go ahead and calculate that. So I'm getting negative 227.15. This has 3, so I guess we would go with just 3 based off of the mass amount. So QAQ is going to be negative 227 joules. So what does that mean about Q solution here? What's the only difference? It's positive 227 joules. Now, solving for delta H, one other added little thing that we have to remember is delta H is going to be expressed in kilojoules per mole. Kilojoules per mole, that's how we always express delta H. So I'm going to take this and go ahead and immediately convert it over to kilojoules. Just divide by 1,000, 1, 2, 3, so this is 0.227 kilojoules. Okay? So that's going to be what goes on the top, the Q solution, in kilojoules. Should put it that way. Okay? So once you get your joules here, convert it over to kilojoules. Now we need to know the moles, and we only want the moles of the solute here. So we're going to focus on finding the moles of the solute. KBR, we need the periodic table to look up the molar mass. So let's go ahead and do that. So KBR, K is going to be 39.10 grams, and then the bromine is 79.9 grams. If you look those up on the periodic table, round it to 2 decimal places so that we all have the same value. So KBR is 119 grams per mole. Let's go ahead and convert those grams over. So I'll do it up here since I'm running out of space. We have 1.34 grams KBR, 119 grams per 1 mole of KBR. Go ahead and divide that. We end up with 0.0113 moles KBR. Now I know my moles, now I know my kilojoules, now I can plug in down here. So I'll do it over here. We do 0.227 kilojoules over our 0.0113 moles, and delta H ends up being, so we went with 3 significant digits there, so 20.1 kilojoules per mole. That's going to be our final delta H. And it's positive. And what do we know about delta H in terms of endo processes? What's always the sign on a endo delta H? It's from a couple notes ago, a couple lectures ago. What's always the sign for an endo delta H? Like products minus reactants, absorbing, then heat. The product's heat should be higher than the reactants. So your endo delta H should always be positive. If it's exo, your delta H should always come out negative. And that's how you can kind of construct to see if you're doing this right. Temperature drops, that's endo, okay? Delta H needs to be positive as well. So these things should match. Temperature dropping, delta H should be positive. Delta H is always positive for endothermic processes. Make sense? These ones definitely have a lot of steps. Find the solution, the aqueous, the water. That's kind of like the surroundings perspective. Change the sign, change it to kilojoules, divide by the moles. You'll get your delta H. So a lot of steps here. There are some practice in your problem set to do these. So we're correct with our answers there. 2 more exercises to look at. Exercise 10 is similar to exercise 11. The only difference here is we have a reaction taking place now instead of just dissolving. We were just dissolving the potassium bromide salt. Here we're actually reacting stuff. Because we're taking 50 milliliters of 0.1 of silver nitrate. We are reacting with 50 milliliters of 0.1 of the HCl. So we have a reaction taking place. We're getting a product over here. You put the two together, you mix it up, and you see the temperature of the mixture increases. Goes from 22.3 to 23.11. What does that tell me about what type of process is going on here? Is this endo or exo? This is exo, good. Identified it. So what does that mean about my delta H? When I finish calculating for delta H, what should be the sign on the delta H? Yes, delta H should be negative, and if it's not negative, I know I've done something wrong. All right, let's keep reading. Delta H for this reaction of silver nitrate, assuming the combined solution has a mass of 100 grams, specific heat of 4.18, just like water. Once again, the majority of the stuff in there is water, so that's why it takes on the same specific heat as water. Because 50 milliliters of 0.1 solution is not a lot of the substance dissolved for either the acid or the silver nitrate. The majority of stuff in there is actually water molecules. All right, so it's the same thing as what we did before. Now we're going to be dealing with the QAQ always first. Let's get that amount, go from there. So QAQ equals MCAT. What did it tell us? Yes, we are looking at finding the mass of the solution. And luckily, since it gave us milliliters and molarity and all of that, instead of us trying to figure it out, they just tell us what the final mass of the solution is here, 100 grams. So we don't have to figure that out. That's given to us. That's a nice little added tidbit, 100 grams. Specific heat, they tell us that part. Now we have to do the final temperature, 23.11. I guess I should put in the things there. All right, now we can find QAQ. Oops, I guess I need to subtract my initial temperature. Let me do that too, 22.3. Not forget that. We calculate our QAQ. 100 times 4.18 times the 2311 minus 22.3. Not a whole lot of temperature change, but here we go. 338.58. This has 4. The measured values here, these ones have 4, so I'm going to go with 4. So 33.58 or 33.8.6 joules. This equals QAQ. So what is going to be our Q reaction then? What's going to be the Q reaction if QAQ is 338.6? It's going to be negative. Just change the sign. Very good. And this is in joules, so I'm going to immediately convert it over to kilojoules just by going 1, 2, 3, 3386 kilojoules, so that I'm ready to go for my delta H. Well, here we're looking at the measured values. These ones both have 4. This one has 4. This isn't really a measured value. That's a constant value, a given constant value. So that's why I'd go with 4. Once again, though, if in doubt, use 3 significant figures, because that one's the best chance of being within 1. All right, so now we have the Q reaction that is negative, which I need to make negative here too. So this equals negative kilojoules. Good. We have that part done. All right. So ready to go for this part. Let's look at the moles. Okay, and we're looking at our reactant here, which happens to be the silver nitrate. I need to find the moles of that. I need the moles of the reactant. How do I figure out the moles of the reactant? What information did they give us there? They gave us molarity and volume up here, so we can figure that out. Okay, the molarity and volume. So we got 0.0500 liters. Can change that over. You can use the molarity equation too, just like this. If you want to use it this way, that's fine. I like to use my T-charts because it helps me set up for other stoichiometric type problems. So it ends up being 0.00500 moles. So now we know the moles of the AgNO3 of our reactant there. So now it's really just the Q reaction over the moles of our reactant, which is the AgNO3. That's going to give us our delta H, okay, of reaction. So we plug that in, we get the 0.3386 kilojoules. Don't forget your negative over here. Divide it by the moles. And this time I'm going to go with 3 because the moles have 3. So ultimate end for our delta H here is going to be 67.7 negative kilojoules per mole. So that's what I would do there for that particular one. The reaction one, same idea here. Following the same steps, you find QAQ using all the information about the combined solution, which is measuring it from the surroundings, the thermometer and everything. Switch the sign to get the Q of the reaction or solution divided by the moles of the reactant or the solute. You get your delta H reaction. Reactions can be carried out in a sealed bomb chamber. This is called bomb calorimetry. That's what it looks like. Now we don't have anything complicated like this in our lab. We use the coffee cup idea with the styrofoam. But they have an insulated container. They have a bomb chamber. Okay, the bomb chamber here that has the reaction sample in there attached to these electrodes, of course, so that you can hook it up and give it a little spark to get started in there. And then, of course, it's surrounded by the water. You do have a stirrer, okay, that's going to stir it up. You have your thermometer, which is, of course, from the surroundings perspective. And, you know, this is how they can carry out some reactions in there. Measure up how much it heats the water. How much does it heat the water? And I mean, it's kind of under the idea of bomb calorimetry that we are combusting stuff. These are like exothermic reactions taking place in here. It's going to heat up the water, you end up figuring out the delta H of that particular combustion. So the heat absorbed, technically, I guess you could use it for finding it if it cools down as well, but usually these are exothermic because they're combustion reactions. Is a very good way to approximate the enthalpy change. And remember, enthalpy change is just the wordy version of delta H. Delta H is enthalpy change. Okay? So this is how we figure it out for these combustion reactions that we wouldn't be able to dissolve in solution. So they have to put it in the chamber and they can figure out delta H from there. Different feature is we use this equation here. The Q reaction is equal to negative C-cal times delta T. Now, Q reaction is the heat evolved by the reaction, assuming it's exothermic, so it's transferring heat to the water here. The C-cal is the heat capacity of the bomb calorimeter, so they have to do some testing to figure out what the heat capacity is of that first. But do notice that they put the negative in here for you to automatically make your Q reaction negative, because we're going to assume if the water's heating up that the initial temperature is less than the final, so your delta T should be coming out positive here for these exothermic combustion reactions. So like I said, I haven't really seen problems like this where they're using it to find an endothermic reaction, because usually this is for combustion type things that you wouldn't be able to put in solution and figure out. It has to take place in the chamber. So we would use Q reaction equals negative C-cal times delta T here. Let's go ahead and work a problem like this. We're combusting methyl hydrazine, CH6N2, liquid rocket fuel. Here is our balance reaction of what is happening here, okay? Now, when 4 grams, that's the amount that's put in the chamber here, 4 grams of the methyl hydrazine is combusted in a bomb calorimeter, the temperature increases from 25 to 39.5. Separate experiment, the heat capacity was measured to be 7.794 kilojoules per degrees Celsius. Now it's nice that they already made this in kilojoules for us, then we don't have to convert it at the end there. So it's already in kilojoules for us. And we want to calculate the heat of the reaction of, for combustion. So now this is like delta H combustion here. We're calculating that for our methyl hydrazine. So the first step, of course, is using the Q reaction, which is negative C-cal times delta T, okay, like so. Well, we know our C-cal, they told that to us, and we know our temperature change, so we can easily fill that in. So this is negative 7.794 kilojoules per degree Celsius times the 39.5 minus the 25 degrees Celsius. This is going to give us our Q reaction. What you should notice, of course, is that the degrees cancel, so we're going to end up getting kilojoules over here. And because they put this negative in front, it already changes the sign for us. We know it's exothermic because the temperature increased here, but it already changed the sign for us, so we don't have to do the changing of the sign here. So I'm getting 113.0. And these have 4, so this has 4. I'd go with 4 here as my Q reaction. The next part is finding the moles of our methyl hydrazine. So we need to find the molar mass of this. Let's go ahead and calculate that out. So that's 12.01 for the carbon. The 6 hydrogens is 6.06 because each one's 1.01. And then the nitrogen 14.01 times 2 is 28.02. So we add that up and we get our molar mass here. And I get 46.09 grams per mole. This is the molar mass. Now I can take my 4 grams and convert that to moles. So 4 grams of the CH6N2, 46.09 grams per 1 mole. Or this not 2, that's a 1. Oop, it erased my C. CH6N2, CH6N2. So 4 divided by 46.09, that gives me 0.08679 for my moles. Now I can do my Q reaction divided by my moles, and that's going to give me my delta H reaction. So let's plug that in. We get 113 divided by 0.08679. And going for those 4 significant figures, because there's a lot of them in there, I'm getting 1302 kilojoules per mole. 13.02. Now you can convert that to scientific notation as well if you prefer it to be that way. Go over 3 kilojoules per mole. So what you should notice in the pattern of these 3 problems, although the last one is slightly different, you should notice that it's going to be the Q, the heat evolved, divided by the moles. That's the end thing to calculate delta H, and it should be in kilojoules over moles at that point. Bomb calorimetry, you don't have to change the sign because they already give you the C-cal, negative C-cal part of the equation. In solution or like a aqueous reaction like the silver nitrate acid one, both of those you're finding QAQ and you change the sign to find the Q reaction or Q solution. So the rest of it's very similar. Following those same steps. Bomb calorimetry, they already basically do the sign for you, and if the heat capacity of the bomb calorimeter is already in kilojoules per mole or in kilojoules per degree Celsius, you don't have to worry about changing that either. So similar problems, not exactly the same thing as warming and cooling. Watch the thermometer, which way it goes. We got a negative. Oh, and I forgot the negative. Nobody even called me out on the negative. This is supposed to be negative, remember? Negative, negative. Why? Because it's exothermic. Our delta H is supposed to be negative. So, remember, exothermic, negative delta H. Endothermic, positive delta H. So don't forget your sign. Sign's always a problem. This unit is the unit of signs. Make sure you get the right sign at the end.